Okay, so now we're going to talk about the Riemannian measure. Um, so if you go ahead and look at the the Riemannian metric, it's going to induce a local arc length by basically introducing an inner product in the tangent spaces. This is going to generate a differential version of the arc length, um, and and so this gives us the Riemannian distance as we discussed in the last lecture. So we have a Riemannian metric. There's also a natural way to introduce a measure on the manifold. And how this is done is essentially um, we want to essentially construct a unitary diagonalization of the Riemannian metric. So essentially, we want to find an orthonormal basis of the tangent bundle in local coordinates, of course. So we can't necessarily construct this orthonormal basis globally, but in local coordinates, we can find an orthonormal basis, which such that, like say EI, such that G of EI EJ is delta IJ, okay? And the reason why we can construct this is due to the spectral theorem, because in local coordinate charts, we can express G as essentially at a single point, okay? G is essentially going to be, in coordinates, is going to be a positive, definite, symmetric matrix, and so it's normal. So by the spectral theorem, it admits a unitary diagonalization, which means that we can find this orthonormal basis in local coordinates, and also just due to the fact that it's a smooth manifold, the metric is smoothly varying. This orthonormal basis will also be smoothly varying with respect to this coordinate system. Okay, so once we have this orthonormal basis, and ortho meaning orthogonal, normal meaning of unit magnitude. So that means that G of EI is equal to 1. Then we can define the volume of the unit cube to just be 1. Okay, so essentially we construct the unit cube and using this orthonormal basis and declare that its volume is 1. And then we can essentially find the volume of any parallelepiped in the tangent space, because if you take any parallelepiped, then you can express the vector frame which frames the parallelepiped in terms of this orthonormal basis. And you're essentially, let's suppose that our vector frame is actually the partial I, these partial I's which are given by the coordinate frame. Okay, so we have this coordinate frame of the tangent space, and we want to ask the question: what is the volume of the parallelepiped, which is framed by our coordinate vector frame? And the answer is, well, there's this matrix of coefficients which relates this orthonormal basis, which is a unitary diagonalization of the metric, um, to our coordinate frame, and that matrix is essentially the determinant of that matrix is going to be the volume of that parallelepiped. Okay, now this is an important thing, is that if we look at the definition of G, and now let's just look at kind of the unitary diagonalization. Well, if we diagonalize with a basis of eigenvectors that are orthonormal, then we're going to get some diagonalization, let's say A transpose, or A dagger, right? So A dagger in local coordinates, but this diagonal matrix is just going to be the identity matrix. So um, so we get that G is equal to A dagger, basically, which in local coordinates, right? And so this means that with respect to these local coordinates, the determinant of G, where G is expressed, of course, in terms of its tensor components with respect to this coordinate basis, not with respect to the orthonormal basis, but expressed in terms of its tensor components Gij with respect to the coordinate basis, then the determinant of that matrix is precisely the determinant of A times the determinant of A transpose. And this matrix A is going to consist of these, of essentially the projection of these, the projection, it's going to precisely consist of the projection of these coordinate basis vectors onto the orthonormal basis, okay? So what does that mean? Well, that means that that the determinant of Gij is precisely the determinant of A squared, where the determinant of A is going to be the volume of this parallelepiped spanned by the coordinate vectors. Okay, sorry, yeah. So what that means is that the volume of the parallelepiped spanned by the coordinate vectors is precisely the square root of the determinant of G, Gij, where Gij is the matrix, the 0-2 tensor expressed with respect to the coordinate basis, okay? So we have this scaling factor, the square root of the determinant of the metric tensor. And so the integral, so then we can use this to essentially define the integral over a coordinate patch. So if we have a function that's supported in a coordinate patch, entirely in a coordinate patch, then we can define the integral of that function over M with respect to this Riemannian volume measure as simply the integral over the coordinate chart of the pullback of this function via the coordinate map, and then but scaled by the square root of the determinant of the metric. So it's going to be like integral over M of f dv is equal to the integral over var phi of u, or var phi is the coordinate map, integral over var phi of u of f square root of the determinant of g pulled back by var phi, and then integrate with respect to the Lebesgue measure on Rn, on the coordinate system, okay? And you can prove that due to the fact that the metric transforms tensorially, so the metric will transform tensorially according to the formula G prime is equal to G conjugated against the Jacobian its transpose. So like G prime is equal to J dagger, where J is the Jacobian of the coordinate transformation. So due to how the metric changes or transforms, this definition is actually independent of the choice of coordinate charts. So this definition of the integral, okay? So we want our integral to be independent of the choice of coordinate system, and you can use the change of variables theorem to show that indeed this definition, because of the way that we've introduced this square root of the determinant of the metric with respect to the tensor components of the coordinate system, that definition is independent of the choice of coordinates, because when you apply the change of variables formula for integration over Rn, you're going to get that this determinant of the Jacobian factor, which pulls up in the change of variables formula, this determinant of the Jacobian is precisely going to cancel out with the way that the metric, the determinant of the square root of the determinant of the metric changes in this coordinate system, okay? So this way you can define a coordinate independent integral, and on an oriented manifold, the definition is, there's an equivalent definition, which is essentially, okay, first of all, on an oriented manifold, you can just define in coordinates, you can define a volume form. You can define a volume form, which is just the square root of the determinant of G, then dx wedge, dx1 wedge, dx2, etc., wedge dxn. So you can use the wedge product to define a volume form when the manifold is oriented, and you can define this in local coordinates. And then you can essentially extend all of these definitions to integration on compactly supported functions of a manifold just using partitions of unity. And once you can integrate functions which are compactly supported on the manifold, then you can construct a more generalized notion of the integral by essentially completing that space of integrable functions with respect to the norm. And so that, if you have the L1 norm, you can complete with respect to the L1 norm. You can also complete with respect to the LP norm in general. And that will give you a space of integrable functions over the Riemannian manifold. And then one last thing is that this definition, this definition of the Riemannian volume element, namely, it's basically you have the Euclidean element in coordinates, the Euclidean element in the coordinate chart, scaled by the square root of the determinant of the metric. There's a way to define this which is independent of the coordinates, which essentially uses the inner product on the tensor bundle that we discussed, I believe, in lecture 2. So you take this inner product over the tensor bundle, and you use that to define a metric, right? You get a metric on the tensor bundle, which allows you to define a notion of length. And then you just take the length of, so then you just take the length of just partial 1 wedge partial 2 ... wedge partial n, where the partialize are the coordinate vector frame. You just take the length of that tensor of the wedge product of the coordinate basis vectors. The length of that tensor is precisely going to be your volume, the volume of the parallelepiped spanned by those vectors. Okay, so that's and those definitions agree. Now remember the wedge product is the anti-symmetrization of the tensor product. Okay, so now let's talk about the gradient of a function. Okay, so if you have a function on your manifold, then you can define its differential df by taking the exterior derivative. And df is essentially a one form, so it's a covector field, which takes in a vector field and spits out the directional derivative of the function in the direction of that vector field. Now it turns out that this is equivalent to projecting onto the gradient vector field of f with respect to the Riemannian metric. So you can define the gradient vector field of a function f just be the sharp map. If you take the musical isomorphism, the sharp, which is an isomorphism between the cotangent bundle to the tangent bundle, you can send this covector field df, the exterior derivative of f, to a vector field called the gradient of f. And this is going to satisfy the property that essentially if you look at the inner product with respect to the Riemannian metric G of the gradient vector field and another vector field, that's precisely going to give you the vector field x applied to the function f, so xf, which is essentially at every point that's a directional derivative of f in the direction given by the vector field x. Okay, so in this way we have a natural way to construct the notion of the gradient of a function. Okay.